In this video, we will cover some of the background concepts and theories that underpin much of the rest of our discussion on gases. In particular, we will be looking at the kinetic molecular theory. So before we dive into the theory of gases, let's familiarize ourselves with what we actually mean by gases. Gases themselves are a phase of matter, similar to solids and liquids. They are composed primarily of particles that are moving randomly and typically, at least at room temperature, at very high rates through their container. Gases move in straight lines until they collide with each other or the container, and after which they bounce off. So our little model here would be those little spheres are gas molecules dramatically zoomed in. So you can see them moving around in three-dimensional space, colliding off of each other, colliding off of the wall. A gaseous atom or molecule exerts a force when it collides. So when it collides against the side of the container or when it collides against another atom, it exerts a force on either the surface or the other molecule. And that surface is what we actually detect as pressure. When it collides, there's a change in momentum. That change in momentum exerts a force, and the way we measure that force is pressure. Now, there are some basic properties that we talk about when we're talking about gases. Right? So the four main properties of gases are pressure. The primary units that we'll be using are Pascal or bar. Those are the SI units. Previously and in your textbook, they use atmospheres. 1 bar is pretty close to 1 atmosphere of pressure. It's 1.01325 bar is 1 atmosphere of pressure. But because the bar and pascals are within the SI units, scientifically it is much preferred to be using Pascal or bar as opposed to the more outdated unit of atmospheres of pressure. Volume is another basic property that we will look at when we're looking at gases. Now, when we're looking at gases, a lot of times things are going to be measured in cubic meters. This is one of the base units of volume. There's also liters, which is much more convenient to work with. 1 liter is a cubic decimeter. And so when we're working with gases, we'll be switching back and forth between going from liters to cubic decimeters and from cubic decimeters to cubic meters. Then there's temperature. We will be primarily using Kelvin, although at times values in questions and problems are going to be in Celsius. Most of the time you'll then need to convert from that Celsius unit to Kelvin. The way you do that as a review is that Kelvin is equal to the temperature that you have in Celsius plus 273.15. And then the last of the 4 basic properties is the amount of substance that we're working with in units of moles. The symbol for that will be N. Now, each one of these properties themselves are interrelated. So the pressure, volume, temperature, and number of moles, as we will see in subsequent videos, they are all interdependent on each other. When you change one, it affects the others. If we double the number of moles, we will, while keeping pressure and temperature the same, for example, we end up doubling the volume. So when one changes, it affects the others. The simple gas laws, which we will be talking about in a later video, describe the relationship between 2 pairs of our 4 basic properties. So like pressure, volume, temperature, number of moles, pressure, those are some of our basic gas laws. So typically for those gas laws, we will be looking at 2 properties while keeping the other 2 properties constant. So looking at pressure and volume while keeping temperature and number of moles constant. Now, the unit of pressure is unique to gases. When we're looking at solids and liquids, we don't have this concept of pressure that we're working with. Typically for those, we still have number of moles, we have the volume that they occupy, and we have temperature, but we don't really have pressure. So the SI unit for pressure is the Pascal. This is a unit that is based on some of the primary units. The Pascal is equal to a kilogram meter per second squared, or a Newton per meter squared. And so that you can see that that's a force spread out over an area. There's a unit that is very much related to the Pascal, which is at times more convenient to use, and that's bar. 1 bar of pressure is about 10 to the 5th pascals. The reason that we will sometimes work with bar is that 1 bar is roughly equivalent to 1 atmosphere of pressure. Some other units that we will be looking at but won't be using as extensively are millimeters of mercury. The unit is mmHg. This is sort of an older unit that is based on how we used to measure pressure using barometers. There's a torr, which is essentially just the exact same thing as millimeters of mercury. 1 millimeter of mercury is 1 torr. They are, for all intents and purposes, the same. Atmosphere, this is an outdated unit, but one that is still widely used. So if you're looking at other videos or textbooks, a good number of them are using atmospheres, though to be current with the current scientific lingo, we should be using Pascal. Pascal is the SI unit, and that's the unit that we should all be using. Now we can convert between any 2 pressure units as long as we know how they're related. As I said before, millimeters of mercury and torr are the exact same thing. So 1 millimeter mercury is 1 torr. Typically, at atmospheric pressure, you have 1 atmosphere, and that's going to be at 760 millimeters of mercury. So 760 millimeters of mercury is equal to 1 atmosphere, and because 1 torr is the same as a millimeter of mercury, 760 torr is also 1 atmosphere. 1 atmosphere is equal to 101,325 Pascal, and because 1 bar is 10 to the 5th Pascal, that means that 1 atmosphere is 1.01325 bar. Now that we have an understanding of some of the different ways that we measure gases, it would be helpful to have a conceptual model for how we can view gases and use that to predict behaviors. So the primary one that we will be using is the kinetic molecular theory of gases. It's a conceptual model that envisions atoms as being hard spheres. You can think of them as little pool balls or glass marbles or something like that. Essentially, they're hard spheres. They will interact through collisions. So down here we have 2 pool balls hitting each other. They collide in the middle and then go off through an elastic collision. That means the total kinetic energy that they had going in is the total kinetic energy that they have coming out. Now, this is sort of what underpins the ideal gas model, the kinetic molecular theory. It says that the atoms are in ceaseless motion. They never stop. Once they collide, they come off with some kinetic energy. The energy itself is stored only in translational movement. For the ideal gas model, no energy is being stored as rotational and vibrational energy. Now, if you think back to the first semester of general chemistry, you have bonds that bend and stretch, and that's how they interact with light. Ideal gas model, it sort of simplifies the kinetic molecular theory by removing our consideration of rotational and vibrational energies. If you compare the rotational and vibrational energy to the amount of energy that's stored in translational motion, at room temperature, the vast majority of it is translational, which is why we can make an approximation that there, for all intents and purposes, is no rotational or vibrational energy. It's used to simplify the math and make things easier to predict, but if you're going for high accuracy, you would have to take the rotational and vibrational energy into account. So what underpins the ideal gas model is also lines up with the kinetic molecular theory. Atoms themselves undergo elastic collisions. They don't come together and they stick, right? So they collide and they come off. Now, for the ideal gas model, we ignore intermolecular forces. So for our ideal gas model, there are no intermolecular forces. So if you had 2 charged species, They don't actually attract each other if they're opposite charge or repel each other if they are like charge. This is an oversimplification of what really happens. If you did have two charged species in the gas phase, they would either attract each other if they were opposite charge or repel each other if they were like charge. But that complicates the math, and so we can, to a large extent, ignore those intermolecular forces. We will see later when we're dealing with very, very high pressures where this will cause problems. This assumption will cause problems. We also make the assumption that atoms don't take up any volume. Typically, for most gases, the vast majority of the space of the container is empty. There are no gas molecules in there. The gas molecules take up very little space. And so we can assume that the individual atoms are taking up no volume, because unless you're dealing with high pressure, they only take up a very, very small percent of the volume. And so mathematically, we can typically ignore the amount of volume that they're taking up. So the ideal gas mole itself doesn't have a thing for accounting for the size of the atoms. We'll see later on when we're talking about real gases at high pressure how this can cause inaccuracies in our predictions. But if you're working with things that are at roughly 1 atmosphere of pressure, typically 1 to about 5 to 10 atmospheres of pressure, this assumption that atoms take up no volume works very well and will give you very accurate answers. So if we're envisioning the atoms as bouncing around in three-dimensional space using our kinetic molecular theory, we'd like to be able to explain how that conceptual model of our atoms being hard spheres bouncing around leads to some of our measurables of pressure, volume, and temperature. So using the kinetic molecular theory, the atoms, when they bounce off the side of the container, they change their momentum. So at one point they have momentum, maybe this one has momentum going to the left, it collides with the container and then comes off going back to the right. So the momentum went from going maybe in the negative x direction to going in the positive x direction. That change in momentum, the only way that you can change momentum is by exerting a force. And if you exert a force on a wall, the wall exerts a force back on you, right? So when your atom collides with a wall, changing momentum, it exerts a force on the wall, and we measure that as pressure, which is why the unit of pressure, the Pascal, is a Newton divided by meters squared, which would be the surface area of the wall that it's hitting, times the newtons, which is how hard it's hitting. Temperature is a measure of the kinetic energy of the molecules. So temperature is equal to the mass in kilograms per mole times the average of the squared velocity. So the way you do this is you take your velocity, square it, and then take the average of those values, divided by 3 times our ideal gas constant. Now, because the temperature is equal to our equation here, if you look at the top, this top is essentially kinetic energy, mass times velocity squared. So what this is saying is that at a particular temperature, all gas molecules have the same kinetic energy, right? And that fits in with our kinetic molecular theory of gases. The atoms themselves, when they collide with a container or with a thermometer, they exert some force onto that container, increasing the kinetic energy of the molecules of the glass of the thermometer. That glass then collides with a liquid in the middle, making it move faster. It then takes up more space, pushing the liquid towards the top, registering as an increase in temperature. Right? So temperature itself is a measure of the average kinetic energy of molecules. What this means is that all molecules at a specific temperature have the same kinetic energy. What it does not mean is that they are all moving at the same speed, right? So if everything has the same amount of kinetic energy and we are looking at 2 molecules, one that has a lot more mass than the other, the one with more mass has to be moving slower in order to maintain the same value. R is a constant. So if m goes up, our v squared has to go down. So the more massive the molecule is, the slower it is moving at a particular temperature, but it has the same kinetic energy. So if we compare like methane versus hydrogen, methane is CH4. That is much more massive than hydrogen, H2. So the hydrogen atoms would be moving at a much higher speed, a much higher velocity, because the mass of them is much less at a particular temperature. So if we're looking at a particular temperature, comparing methane to hydrogen, the methane will be moving slower than the hydrogen because the methane itself is more massive. But the methane molecules and the hydrogen atoms, or the hydrogen molecules, have the exact same kinetic energy because it's the mass times the velocity squared, and that's what we're measuring when we measure temperature. The volume is related to the mean free path, which is essentially how far the molecules can move before they collide with another molecule. Right? The higher the temperature, the faster they're moving, and so the more frequent they're going to collide. The higher the pressure, the more they're colliding with the wall, and the more the number of moles of gas, the more atoms that are in the way, which ends up reducing the mean free path. But essentially, when we're talking about volume for a gas, we're really looking at how far the atoms travel before they collide with something else.